Assalamualaikum warahmatullahi wabarakatuh. So we from group 2 to present our project with title Flash Design for Separation of Binary Mixture of Benzene 1 and n-Hexane 2. Flash distillation is also known as equilibrium distillation. The basic principle involved in this type of distillation is flash vaporization, which involves sudden vaporization of hot liquid mixture to be separated by passing it from a high pressure area to a low pressure area. This results in sudden pressure drop, which reduces the temperature of the chamber, which in turn results in sudden vaporization of the liquid mixture. This separation is a common challenge in the chemical industry, particularly in processes such as the purification of hexane for use as a solvent in polymerization reactions, where benzene is an undesirable impurity. The close boiling points of n-Hexane 69 degree and benzene 80.1 degree and their tendency to form an azeotropic makes simple fractional distillation ineffective. This necessitates the use of more advanced and energy-intensive techniques. So, our objective is to design a flash separating mixture of benzene and hexane. Furthermore, to review the processes and typical process conditions for separating the mixture, which include overall composition, operating pressure and temperature. And last one, to calculate the moles of liquid, moles of vapor, liquid phase mole fraction and vapor phase mole fraction. So for our process condition, the suitable temperature used for the flash separation in between 85 degree for our assumption. According on the research, the practical pressure used must be greater than the atmospheric pressure, which is 101.3 to 5 kilopascal. Thus, assume 140 kilopascal where benzene and n-Hexane produce azeotropic mixture, and their separation by flash distillation methods at normal atmospheric pressure is impossible. So, the common use of overall composition is 0.5 over 0.5 for generally test mixture between benzene and n-Hexane.
Next part, we move on to the general equation. For this general equation, we use the formula of fugacity vapor equals to fugacity liquid. Fugacity vapor referring to Yi, Vi and also times with the pressure. Meanwhile, for the fugacity liquid, which referring to Si, gamma I and Pi saturated for every I species. For the next part, we assume the mixture is an ideal solution and also achieve 100% separation for both liquid and vapor. For the second one, we assume the activity coefficient and fugacity coefficient equals to 1 as it is an ideal solution. Now, for the calculation of mole of vapor, liquid, and also the mole fraction, we need to specify our process variable. For inlet stream, we propose that Zi equals to mole fraction of the species I. And also, meanwhile, for the output stream, we have L, V, Si, and Yi. And also, for this flash calculation, we use the basis of 1 kilomole per hour solution mixture fed into the flash column. For the next part, we list down the important equation that we're going to use for the flash calculation. This equation involves mass balance and iteration equation. Next, we also use Antoine equation and also the equation of pressure bubble point and pressure dew point. Next part, we also use the K equation in order to find the mole fraction ratio. And also from this K equation, we can determine the mole fraction of each species. For the next part is the flash calculation. In order to calculate the flash calculation, we need to determine the P saturated by using the Antoine equation. All of the constant value can be determined by using the table B2 in the textbook. And also we define the temperature is actually at 85 degrees Celsius, and we insert all the value, then we get the P saturated 1 and P saturated 2 for both of the component. And for the next part, we also want to calculate the P bubble and P dew point. In order to calculate P bubble and P dew point, we need to determine the Si and Yi. Since we assume the Si and Yi is equal to Zi, which means 0.5. Then we insert the value into the equation and we can obtain the pressure bubble point and pressure dew point. Next, we want to determine the K value by using this equation. By using this equation, we insert the known value and we can obtain the K value for each of the component. For the next step, we want to calculate V and L value, which is referring to vapor molar and liquid molar. By using an iteration equation, we can obtain the V and L value. Now, for the next part, we use all our known information in order to calculate the molar composition for Y. Based on this equation, we already obtained a lot of known information and we can obtain the Y composition for each of the component. From Y composition, we can obtain the X composition by using this formula in order to determine the value of X. For the last part, we want to check whether our calculation is accurate or not. We use the formula of total composition must be equals to 1. From our calculation, we already proved that the total composition for each of the liquid and vapor is equal to 1.
Next, we have the TXY diagram for a benzene and n-Hexane binary mixture at 140 kPa. On the far left, pure n-Hexane boils at 79.37 degrees C, while pure benzene on the right was at 90.88. Then we have the PXY diagram for the same benzene and n-Hexane system. From this diagram, we can pinpoint the saturated pressures for both pure components. The saturated pressure of pure n-Hexane is 164.54 kPa, while the saturated pressure for pure benzene is 117.895 kPa. As observed from the phase diagram, at a mole fraction of 0.5 and the pressure of 140 kPa, the mixture exists in the two-phase region. Hence, 140 kPa is an optimal operating pressure for achieving effective phase separation. Next, we have PFD for flash drum with an inlet molar flow rate of 1 kmol per hour. This feed is an equimolar mixture of benzene and n-Hexane. Based on our earlier TXY diagram, a mixture with this composition will remain completely in liquid form as long as the temperature is kept below 79.37 degrees. Therefore, we have assumed an inlet feed temperature T of 75 degrees C at pressure of 140 kPa. Inside the flash drum, heat energy Q is added to partially vaporize the mixture, bringing the system to a temperature of 85 degrees C at 140 kPa. This causes the stream to split into two phases, which is vapor and liquid with mole fraction calculated before. Now let's look at the mass balance to verify our calculation. Based on the data, we set up two simultaneous equations for our components. The benzene balance is written as the equation 1, while the n-Hexane balance is equation 2. By solving these two equations together, we find that our liquid flow rate N2 is 0.6847 kmol per hour and our vapor flow rate N3 is 0.3153 kmol per hour. This is similar with the flash calculation where the vapor is 0.3154 kmol per hour and liquid is 0.6846 kmol per hour. Now let's look at the total mass flow rate, where we converted the molar flow rate into mass flow rate using molecular weights. For the inlet stream, the total mass flow rate is 82.1455 kg per hour. And looking at the outlets, the sum up both outlet streams together, they are equal with the inlet mass flow rate, which is 32.1455 kg per hour. Next, we calculate the heat required by the system. First, we choose our reference state at 75 degrees C and 140 kPa in liquid form, which make the inlet enthalpy 0. By applying the general energy balance equation and assuming no work done, no change in elevation and no acceleration, the equation simplify directly to Q equal to delta H. Based on our calculation, the required heat input Q for our flash drum is exactly 3.0620 kW. To summarize everything, flash drum was used to separate an equimolar benzene and n-Hexane feed with the molar flow rate 1 kmol per hour at choosing condition. The separation produced 0.6847 kmol per hour of liquid and 0.3153 kmol hour of vapor. The liquid stream contains 0.5262 kmol per kmol of benzene and 0.4738 kmol per kmol of n-Hexane. The vapor stream contains 0.4431 kmol per kmol of benzene and 0.5569 kmol per kmol of n-Hexane. With the inlet stream temperature assumed at 75 degrees C, a thermal load of 3.0620 kW is necessary to achieve the target temperature of 85.85 degrees C. Overall, the results show that flash distillation can effectively separate the benzene and n-Hexane binary mixture under the chosen condition. That's all from our group.